Welcome back to the third and last part of this series on the basics of virtual analog modeling. And as I mentioned before, in this part we're gonna implement the circuits that we modeled. And yes, I'm gonna create a module for PCB rack. Well, actually, I'm not gonna create a new one. I'm gonna use my prototype model, which is the one that I usually use at the developing stage. So I have this module that has like a bunch of knobs, modulation inputs, and also inputs and outputs and switches. So I usually just before starting designing a GUI or anything, I use this one for testing, and we're gonna use it. Okay, so one thing that I need to correct before continuing, it was in my crossfader model. I forgot that I needed to add a gain compensation stage. So the curves that we're having were had a very low gain, and this crossfader circuit needs this operational amplifier in order to return the signal to an appropriate level. And so what I did to analyze is exactly the same. The main difference is that here we have an operational amplifier, and this operational amplifier, I have to use a model, and since I'm not modeling anything special about it, it's a very ideal model. And the way I describe it is just like input gain, the difference of the voltage times a gain. So when I start making the analysis, I get this term, which is the gain of the operational amplifier. And once I obtain the equations, they are in function of the gain, and then I can just use Mathematica and calculate the limit, the mathematical limit when this gain tends to infinity, which is the operational amplifier, and that gives me back this simplified function. And here I have this is gain of voltage 1, gain of voltage 2 for the crossfader, and this is the plot that we get, which is normalized to 1. And these are, and after a bit more simplification of this, I get these two values for the gain. So the way the code of this prototype is organized, I have a main process function that receives all the 8 inputs and returns all the 8 outputs. And all these inputs are normalized to 1. So whatever is in VCV rack is 10 volts, here I'm going to receive just a signal which is in the range of 0 to 1. Then I have the parameters which are set. I'm only using 4. I have 4 parameters, and I have a modulation. And all these are just auxiliary functions to initialize all the internal variables, and these ones are used to set the knob values when they change, or set the modulation values. And there is nothing special about it. So the only thing that we need to do is to update, to add code here. So let me run it the way it is now, and all the inputs are being bypassed. So if I connect one oscillator here, we can see the output, and this is the second oscillator, and these are the oscillators that we're going to use in our crossfade exercise. So to make that, this is actually pretty simple. We receive, we're going to create a function, this crossfade, and we're going to receive the signal, the voltage 1 and the voltage 2, and a parameter which is going to be the position of the knob, and I'm gonna call it, I think that here it was called P for position of the potentiometer. And what I need to do is just return one signal. Well, first I'm gonna calculate the gains. the gain one is this one. I can, since these are very simple formulas, I can just copy paste. But there is like an issue if you have used the Volt language before. This first we need the multiplication signs, and then we also need to convert these numbers to real values, because these are considered integers, and the Volt language refuses to compile these numbers. So the next thing that we're going to do is calculate the gain 2, which is straightforward as well. Just take this formula, put it here. Let me add all the necessary stuff. So, okay, we have calculated the two formulas, the two gains. And if you remember, it's just the gain K1 times V1, gain 2 times V2. So let's just return that value. K1 times V1 plus K2 times V2. And let's plug our code here. So the output 1 is gonna be a crossfade of the input 1, input 2, controlled by the first parameter, this one. So yeah, on the VCB rack side, this prototype module it works already. So I just need to compile and install, and let's test it. Let me disconnect. And we can see that our crossfade is working. And let's listen to it. And let's add an LFO. To control it, and there is one thing that we need to take care, that this is valid for a p value that goes from 0 to 1. But fortunately, I'm already clipping the value at this point. Otherwise, I'm gonna duplicate it. So this is gonna be my p, the p input. P is gonna be clipping from 0 to 1.0. That way I can reuse this function, and it's never gonna be outside the valid ranges, and it's gonna work. Okay, like this. Okay, this was a very simple example. We didn't need to write anything special or a simulation. It was just, it's a static model. We just needed to write the formulas. Now let's go with our RC filter. So what I'm gonna do is, I'm gonna write it here as well. So this is gonna be my RC filter that takes as parameters the input, and then the position of the potentiometer. I'm gonna use the letter P as well. Well, here I use U. Let's go with U. And first, we have to calculate the derivative. which is the derivative of vc, it's equals to all this thing. So important, well, let me fix just the numbers, the multiplications. Important. So we have, we use vc, and this is our state. And what we need to do is actually declare a variable memory. So if you don't know what I'm talking about at this point, you have to watch my other tutorials on coding a module in the Vult language, where I did like a few simple things, and all these concepts were explained. So what we are having here is it's a VC. It's a value that is remembered once the function is executed. And the input, I call it I. This is U. And so far we're calculating the derivative. And if you remember the previous video, I was talking about that we needed to integrate the derivative in order to calculate the value of Vc. And here is where the simulation parts comes. And in the previous video, I showed you as well like the different simulation results based on the simulation method. And I show you the simplest simulation method, which was the Euler. And yeah, you can find more information here, but you have to know that there are other methods like Ronquetuta, or also the Hune method that I presented. And there are other more advanced methods. So depending on the characteristics of your simulation model, you will need to use one or the other. In this case, I'm gonna stick to the simplest method, which is the Euler. And let's start with this one and see how it goes. So basically, this method, with this calculating the output in this method, is reduced to this formula. So the next value, it's of the output is the current value times h, where h is the size of the step, multiplied by a function of the time and the output. So this is what basically it is saying is, I will directly code it. Our future value of Vc is going to be the value of Vc plus h, which is our step size, times the derivative of Vc. And this is it. This is our integration. And well, we need to calculate h, and h, I'm going to calculate it straight here. H is how far we are moving from one point to the other, which is very easy. Calculated is 1 over the sample rate. And if you remember this one, our output, it was our value of Vc. So we just return this one. And here we have a very simple Euler integration. And let's test it. So I'm gonna leave this one like that, and I'm gonna assign it this, and just gonna call it O. These are our oscillators, and the output one is gonna be the RC filter that receives the two oscillators, and it's gonna be controlled by the signal U, which I can use, for example, the input 3. Well, it can be the parameter 2. Let's use the parameter 2. And that's it. Let's see if it compiles. Okay, yeah, it compiles. Let's listen to it. Let me lower the volume. So what's happening? Nothing is happening. Let's check what I did wrong. So we take this input, goes into O, RC, I don't see what I did wrong. Let me just add a number 0. Okay, this is fine. We are not listening anything, which means that the code is running fine up to here. H, let me put a value of 0 here and see what's my output. What did I do wrong? Definitely there's something wrong. Okay, if this value is 0, we get U1 VC has a value. I don't know what I'm doing wrong. Let's check what will be the derivative if we just do this. Oh, that was too strong. Okay, so we have something in the derivative. And derivative times h. Okay, so you have to consider that this is the third video that I'm making during the day. Okay, this seems like it's working. But I disconnected this value, which I said that it was going to be parameter 2. Oh, okay, yes, I know what happened. So this is a clear example of this thing going mad. So what happened is when I move it to 0, this value u, it's 0. Therefore, the value of the derivative is very, very high. Since and this produces a very large derivative value that just makes the whole system unstable. And this is like an effect of this Euler method not being very good. It just becomes unstable quite fast. But if you remember, I can actually make this number larger, and that would be equivalent of setting a larger minimum resistor. So let me take a number 10 and see what happens now. Okay, it seems to be working. And yeah, you can hear that this filter is not closing completely, and that's because of the resistor value that I selected. So let's change the values. So here I set a minimum of 10, and the maximum let's put 10K. And if we run again this, okay, we have an extra equation. This is what we got. And 10,000, 10,000, 1,000. Is it the correct? Oh yeah, it is, it is. So the values in this one is 10,000, 10,000, and 1,000. 10,000, 10,000, 1, and 1,000. So now the value of the resistor can be larger, therefore the filter will be able of closing even more. So if you see this behavior, this is not very good, and this is because we are changing the value of the potentiometer in a linear fashion. So the whole effect of the filter it happens in this part. But one interesting thing about this is that we can use it as a we can take advantage of this. Let me change it a little bit smaller, not 10,000. I'm going to use 5,000. Let's get, okay, it's practically the same. 10,000, 10,000, 1, 500. And what I'm going to do, I'm going to invert the value. Instead of being from 0 to 1, I want it the opposite. That way, when my parameter is in 0, I want it to be closed and then to open aggressively in the last part. I can do it either here or directly here. I'm going to make it here. So this is our fixed value of u. That is just going to be 1 minus u. And we're going to clip it just in case. Even when I have already clipped the value here, but let's put it here. So this new value of uu is exactly it behaves inversely. Okay, now it behaves more like we expected. And now let's use a simple envelope to control this value, which is my parameter tool. And let's use the gate from the keyboard. And we have a kind of bad low pass gate. Yes, so once you have calculated this derivative, you can just change your code and use a different method. And we can see that for this simple filter, this method it's good enough. It's not the most precise, but it's good enough. And the other method that that I talk about. It was the Hume method. So one characteristic of this one is that we need to calculate twice the function of the derivative per step. And therefore it uses a little bit more CPU, but we will gain stability and we will gain as well precision in our simulation. For now, I'm gonna keep it like that, and let's go to the third example that I had. That was the tone stack that we could change only the treble. So I'm gonna remove the filter. Let's implement the tone stack. We have an input and a control signal, which I don't remember how I called. So we have input and and treble. So and if you remember when I made the simplified version, which was this one, these were my differential equations. So I'm actually gonna just take this, copy this, and paste them here. And let's fix the parts that need fixing. So first one, V was my input, so I'm just gonna rename this. And U was my control signal. And then we have VC1 and VC2, which are our states. VC1, VC2. And we needed to calculate the derivatives. And yes, this is our output. And yeah, we have to add the integrator. It's one thing that we can do is create an integrator function. Function integrate. We're gonna receive the derivative. We're gonna have our variable. So I'm gonna call it dx, x, and we know that x is using the Euler method is gonna be equals to x plus h, which is this value, h times dx, and then we just need to return x, and we have an integrator, so we can replace it here. Like this. So one thing that you may notice is that we have this implementation uses twice the memory, but for this example it's just going to be handy, so that way I don't have to write twice this part. So we know that VC1 it's equals to the integral of the derivative of VC1, and the same but with 2. And that's it. We have a simple Euler integrator. We just need to return y, and let's plug it. And we may have the same problem on stabilities, but let's see what results. seems to be working. Let's see what happens if I just add a. So many of these systems may become unstable if we just add like small pulses. It seems like this one is working. What if I add some noise? Okay, it didn't become unstable, but there are other considerations that we need to have. For example, like in this case, this parameter EU, it's enters here and it goes straight into the output. So if it changes very rapidly, this change is gonna be affecting. For example, if we have like some clipping signal, the sharp changes of this thing will go straight to the output, producing like pops and discontinuities. So let's try to reproduce that. For that, let's take a simpler VCO, and I just need a sine wave. Then I'm going to use an LFO with a square signal. You can hear that because of this architecture, the output immediately inserts discontinuities, and there is something similar with the crossfade. It's inserting discontinuities. Since this, what we need to do is either filter these signals, or doing like something more advanced. But let's filter them. We already have an RC filter. We're gonna use it. It's a very simple RC filter, and I'm gonna use it first in the crossfade. So we're gonna filter the parameter, and I want it to be kind of slow. So I'm gonna take a 0.5 value. I don't know what value to that corresponds, but let's listen to. Okay, now you can hear that the modulation is being softened by the RC filter, and we don't have the clicks. Let's do the same with the tone parameter. We cannot hear much because there is no much high frequency content. Okay, but there are no pops anymore. So that's it. Just to conclude, let's make a small recap. And so what I have done here is implementing the differential equations that we obtained using a very simple integration method that for these small examples it's good enough. We saw in the previous video that it may not be the perfect, not be the most accurate, but in order to implement a more accurate model, we will need to spend more CPU. So what you have to do in this case is make an evaluation of, do I really need that accuracy? Does it matter for this specific circuit? And if not, if your results are good enough as in this example, I would say that it's fine. There's no need of sacrificing more CPU. We also saw that some of these parameters that we have in the equations can go, like in this case, straight to the output, which will transmit any pop or any click that we have. If the parameters, if the control parameters will be only as part of the derivative, we don't have to care much because the integrator will soften them. For example, here, this value of u. Actually, let's do the experiment. Okay, no, I'm not. I don't want to make the video longer. So this value of u is possible for it to change rapidly because it affects only the derivative, and the integrator is gonna soften those transitions. And in the third case of the crossfader, we have just like a function that reproduces the behavior of an analog potentiometer or of a network of analog components in order to crossfade a signal and give it that characteristic of the sound. So I hope that you have found this useful. And I would like to make some other more complex models, but that will usually takes much more processing work. You have seen before a little bit of the process that I follow to derive the equations. And in the case of filters or any nonlinear system, this process can be quite tedious because what I try to do is try to come up with the most simplified system of equations that is gonna do the work, and then I have to do all the work of the simulator. And in many cases, I need to implement much more complex integration methods that are very, very tied to the system, and that takes me a lot of time. So I hope that you have enjoyed this quick overview, and thank you for watching these videos. Bye. Subscribe.